So in this video we'll do some identification examples. Now that we learned some molecular geometries and memorized them, now we get to actually practice it. So this entire video cast is just drawing Lewis dot structures, identifying the molecular geometry, and then the angles. So let's start with this one. SF4, this is sample exercise 9.2, which is in page 393 of the digital textbook if you're using Brown-Lemay-Burston 13th edition. So first, SF4, add up the electrons on the periodic table. Sulfur is 6, fluorine is 7, and then multiply by 4, so that's 28 plus 6, so that's 34 valence electrons. Take the least electronegative atom, put it in the middle, and since we know fluorine is the most electronegative atom in the entire periodic table, it's definitely going to go on the outside. Once we've bonded them around, that's 2, 4, 6, 8 electrons we use, so 34 minus 8, that gives us 26 electrons remaining. If I go 2, 4, 6, and then 6, 6, and 6, so 4 times 6 is 24. That's going to use up 24 more electrons to complete the octets for the fluorine. That means I have 2 electrons left. Where do they go? Well, remember, whatever leftover electrons you have, always put them on the central atom. And then if the central atom is third period or below, you can have an expanded octet. Sulfur can have an expanded octet. So now we're supposed to identify the molecular geometry for this. Always look at the central atom to do that identification. And then we find out the bonded and non-bonded domains around sulfur. And we have 1, 2, 3, 4 bonded domains and 1 non-bonded domain. So looking at the chart right here, 4 bonded domains, 1 non-bonded domain. This thing's called seesaw. So my domain name is seesaw. And my bond angles for this, well, remember it's got this equatorial domain right here, and then it's got an unshared pair right here in the middle. And so that would force these bond angles to be a little bit closer. Remember, normally they're 120 all the way around this central portion. So it would be just a little bit less than 120 around this middle portion right here between the fluorine, sulfur, and fluorine. And then right here on this central atom right here, it would be about a 90-degree bond angle right here. 90-degree bond angle on the top like this. So 120 and 90, approximately 120 would be the bond angles. Alright, so that's the first one. Second example, IF5. So first sum the valence electrons. So fluorine is 7, iodine of course is 7, so it's actually 6 atoms that have 7, so 6 times 7, there's 42 electrons in there. End up with the iodine in the middle and bond the fluorines around it. So we have 5 fluorines around the center of this guy. Unshared pairs of electrons around here to complete the octet for fluorine. So this is 8, 8, 8, 8, and 8. So 5 times 8 is 40. We've used up 40 electrons. 42 minus 40 is 2. So that means we have 2 extra electrons to put on this iodine. Remember, iodine is third period or below, so we can go ahead and expand the octet on the iodine. So in this guy, we now have to look at the central atom and then decide the bonded and non-bonded domains to determine the molecular geometry. So there's 1, 2, 3, 4, 5 bonded, and we have 1 non-bonded. So a total of 6 electron domains, so it definitely comes from the octahedral family. 5 bonded and 1 non-bonded is square pyramidal, or square pyramidal. So that ends up having about 90-degree bond angles. These might be squished just a little bit on the side, but approximately 90 degrees for the bond angles. Alright, that's 2 examples. Let's do a third one, SeCl2. So Se is located right here. It's in the same family as oxygen, so that means it has 6 valence electrons. 6 plus chlorine. Chlorine, of course, is with fluorine, so that has 7 times 2. That's 14 plus 6, which is 20 valence electrons for that animal. Put the least electronegative atom in the middle, which is selenium, and then we're going to put the chlorines around it. That uses up 4 electrons gone. Complete the octets for chlorine. That uses up another 12 electrons. 12 plus 4 is 16. So 20 minus 16 means I have 4 electrons remaining. I got to put those on the central atom because this central atom needs to have a complete octet, and now we have octets everywhere. So for this one, if we look at selenium, this one is from the tetrahedral family because it has 1, 2, 3, 4 total domains of electrons around it. 2 bonded, 2 non-bonded. 2 bonded, 2 non-bonded. This ends up being the name called bent right here, just like water. And so this bond angle right here is actually reduced from the normal 109.5 to 104.5. So we'd expect to see a bond angle that is less than the 109.5 that we would normally have. So those are some identification examples. Become good at drawing your Lewis dot structures, identifying molecular geometry, and the angles of those species.